How do we graph y is equal to x squared plus 4 over 2x? Again, let's look at the domain of this function. Find the second derivative. Find the first and the second derivative. Look for critical values for possible local min or max, and then also for points of inflection. Use the second derivative test for concavity at the same time for local min and max, and if the second derivative test fails, then we just use the first derivative to find local max and plot the critical points, and then look for x and y-intercept and additional points. Alright, let's look at this function, and if I again divide the top by 2x, we will see that it's just equal to x over 2 plus 2 over x. This is easier to differentiate. This is just a line, and this is just 2 times x to the negative 1. Take the first derivative, okay? We set it equal to 0 to find the critical values. Now, the first derivative of x over 2 is just 1/2. The first derivative of 2 over x is just negative 2 over x squared. Where did the negative come from? Because this is x raised to the negative 1. So that brings down the negative 1. And then x to the negative 2 brings x squared at the bottom. Now, if you set this equal to 0, that means 1/2 minus 2 over something is 0. What would be that something? Well, if 1/2 minus 2 over 4, which means it's also 1/2, would make it 0, x will be, this whole thing would be 0 if x squared is equal to 4, or when x is equal to plus or minus 2. Now get the second derivative. Y double prime would be 4 over x cubed. Set that equal to 0, and we see that it does not exist at x equal to 0, but we can still test for test for concavity to the left of 0 and to the right of 0. These are what we got. We said that x equal to 2 and x equal to negative 2 are critical values. Please make sure you know how to work that out. You set that equal to 0 and just solve for the x. Now you substitute the critical values into the second derivative using the second derivative test. Okay, y double prime at negative 2 is, of course, that will be negative. Y double prime at 2 would be positive. So at x equal to negative 2, it's concave down. At x equal to 2, it's concave up, which means that a local maximum occurs at x equal to negative 2, and a local min occurs at x equal to 2. Now, the critical points would be plugging x equal to negative 2 here, and x equal to 2 here. And if you solve for y, that's what you get. So what about points of inflection? Again, we already got the second derivative, set it equal to 0. Okay, which means it's undefined at x equal to 0. Right? But let's see why the concavity still occurs on the left of 0 and right of 0. Well, we've already used these two values. This can also be our test points for concavity. Since there is a local max occurring at x equal to negative 2, that means it's concave down to the left of 0. And when we tested using 2 for our x, that's to the right of 0, it's concave up. So that means concave up and concave down means would there be a point of inflection occurring at x equal to 0? Well, what is the domain of this function? Remember, x cannot be equal to 0, so in fact it is it's a vertical asymptote. And so this is how the graph is going to look like if we combine everything. It has a vertical asymptote at x equal to 0. it's concave up to the right of 0, and there is that local minimum occurring at 2, 2. And then x equal to -2, you have a local max occurring there, and it's also concave down to the right of 0. Now, where did this come from? Well, if you look at the graph, if we when we did the division here, another way of writing this is when y is equal to x over 2, it's another way of writing that, plus 2 over x. This x over 2 is the slant asymptote, so that's that line y is equal to x over 2. And so as x approaches positive infinity, the function approaches the line. That's why it looks like that. And then as x approaches negative infinity, the graph will still approach this slanted asymptote. So as x approaches infinity, the y values would approach this diagonal line. So we combined asymptotes and local max and local mins, and then concavity to graph this rational function.